Hello everyone and welcome to a new lecture on Discrete Mathematics. So far we have studied several topics and today I'm going to talk about sequences and summation. So a sequence is simply a discrete structure and we use such kind of structures to represent ordered lists of elements, orders of data. Here order is important. 1, 2, 3, 5, 8. It's a sequence, or 1, 3, 9, 27, 81. What is the meaning of sequence here? It means there is some relation, or you can say the distance between two consequent elements is the same. They follow a form, or we can derive some closed form, and using that closed form we can generate any number of elements following the form. So a sequence can be defined as a function from a subset of integers, like for example you can say from 0, 1, 2, 3 or something to a set of s, and we use this notation to denote the image of the integer n. It means if we give the n as input, what is the corresponding element in our sequence? We can think of an as the equivalent of function, for example fn, that we had already in previous lecture, a function for example from this set. We call this an as a term, right? We call it as a term. Sequences arise throughout mathematics, computer science, and in many other disciplines like AI and in natural language processing. We use such kind of things. So in this lecture, I will introduce the terminology to represent sequences, and also we will study summation and product in order to better deal with the sequences. So here we can see one example. So this is an equals to 1 divided by n. If we consider this as a function, so we give the n, for example, from 1, 2, 3, 4 to the n and find the output. So if we give 1, it will be 1 by 1. If we give 2, 1 by 2. If we give 3, 1 by 3, 1 by 4, and so on and so forth. So this simply is considered as a sequence. There are some famous sequences. We will study some of them like geometric progression, arithmetic progression, and the others. So geometric progression is a sequence of the form ar squared, ar cubed, and so on. So it means we have a, r, and in power of n. Here we have two things, a and r. A and r fixed in all. It is common in all. We call the a as the initial term, and r is considered as common ratio. So a and r is fixed, then n is changed, right? And these two are in real numbers. For example, here we have a equals 1 and r equal minus 1. We find out that bn is 1, 1a. So the first one is 1. The second one is a multiply r. 1 multiply minus 1 is minus 1. This one is 1 multiply minus 1 square is 1. The third one is 1 multiply minus 1 in power of 3, minus 1. The fourth one is 1 multiply minus 1 in power of 4, 1. So in this way we continue. Let's see another example where a equals 2 and r equals 5. So simply we can generate the first or the initial term is 2. The second one is 2 multiply 5, which is equal to 10. The third one is 2 multiply 5 in power of 2, which is 50. And in this way you can calculate the rest. The third sequence, a equals 6 and r 1 by 3. The first terminology is 6. The second one is 6 multiply 1 by 3, which is equal to 2. The third is 6 multiply 1 by 3 power 2, which is 2 by 3. And in this way we can find the rest of the terms. The next sequence is called as arithmetic progression. Arithmetic progression follows this form. And again here we have a, as you can see a is repeated. We call the a as the initial term, and we call d as common difference. So for all real numbers. here, the initial state is 1. In here, the second term is a plus d, where it will be 3. Here, we have a plus 2d. Minus 1 plus 2 multiplied 4 is 7. In here, we have minus 1 plus 3 multiplied 4 is here. So here is the third one. For the fourth one, minus 1 plus 4 multiplied 4 is 15. And in this way, we can find the rest. The next example is a equals to 7 and d equals minus 3. So the first term is 7. The next one is a plus d. A plus d means 7 plus minus 3 is 4. The next one is a plus 2d. A is 7 plus 2 multiplied minus 3 is 1, right? It will be 7 minus 6, 1. And in this way, we continue. A 7 plus 4 multiplied minus 3 will be minus 2. And in this way, we find the rest. In here, we have a equals to 1 and d equals 2. The first term will be 1. The second term will be a plus d, 1 plus d, 3. The third one will be a plus 2d, a plus 4 is 5. And in this way, we continue for the rest. We can think about strings as a sequence of letters. So a string is simply a finite sequence of characters, or you can say letters or symbols, right? Like for example, alphabet. Alphabet is a string because it is a set of letters. Sequence of characters or bits are important in computer science and artificial intelligence. We denote an empty string by lambda, and we have a length as the number of members in a sequence of a string. For example, here 1, 2, 3, 4, 5. So the length is 5. We may have recurrence relations. In here, we find an equation to express it. So in here, an in terms of one or more of the previous terms. So recursion means we have to go back to the previous, right? For example, a1, n minus 1, and we will continue. And here we have n0 as a non-negative integer. A sequence is a solution of recurrence relation if its terms satisfy the recurrence relation. And in here, we have the initial condition for a sequence that specify the terms that precede the first term where the recurrence relation takes effect. So let's see one example. If we have an as a sequence that satisfies the recurrence relation, like an equals to an minus 1 plus 3. What is the meaning of recurrence here? We have an which asks for an minus 1. An minus 1 means 1 before. So if this is one relation, for example, we have 1, 2, 3, 4, 5. A of 3 is based on a of 2 plus 3. A of 2 is based on a of 1 plus 3. In this case, so if this is our sequence and if a0 is 2, then we want to find out a1, a2, a3. So a1 is simply the previous one plus 3. We have already a0 equals to 2, right? So we say that based on this formula, we say an is an minus 1 plus 3. So a1 is equal to a0 plus 3. What is a0? 2 plus 3 is 5. So we find 5. a2 is an minus 1 plus 3. It means a1 plus 3. So simply 5 plus 3 is 8. a3 equals to a3 minus 1 plus 3 is equal to a2 plus 3. What is a2? 8. This is called as recurrence. Here is an example. If we have an is a sequence that follows this one. In this case, an is based on two previous terms, an minus 1 and an minus 2. And we start from 2. It means a of 4 is based on a3 and a2. If a0 is 3 and a1 is 5, so how we can find it? We have already a0 and a1. We want to find a2 and a3. a2 is equal to a1 minus a0. What is a1? 5. What is a0? 3. It's 2. a3 is equal to a2 minus a1. a2 is here, a1 is here. In this way, we can find the terms. Fibonacci sequence is a famous sequence in mathematics. In here, we have two initial conditions. f0 is 0 and f1 is 1. Then fn is the sum of two previous terms. Very simple. f2 is simply the sum of two previous one. Two previous one for 2 is 0 and 1. For 0, it's 0. For 1, it's 1. So sum of 1 is 1. For 3, it is sum of f2 plus f1. What is f2? 1. What is f1? 1. It's 2. For 4 is sum of f3, 2, and previous one, 3. 2 and 3, 5. 5 and 3. And you can see here, in this triangle, we can simply find the Fibonacci sequence. We say that we have solved the recurrence relation together with the initial conditions when we find an explicit formula. This explicit formula, as I already told you, is known as closed form. Closed form will help us to find any number of terms that we need to find for a sequence. We can deal with the sequence using a technique called as iterative. There are two approaches for iterative solutions. One is forward substitution and another one is backward substitution. In forward substitution, we try to find successive terms beginning with the initial condition and ending with an. And on the other hand, in backward substitution, we start with an and then we iterate to express it in terms of following terms of the sequence until we find it in terms of an. When we use iteration, we essentially conjecture a formula for the terms of the sequence. In order to prove that our guess is correct, we need to use some kind of mathematical induction. What is mathematical induction? It is simply a method for proving that a statement is true for all other natural numbers. We will start with forward substitution. This is also known as working upward. Let's see an example here. So suppose we have an, which is a sequence, and it's a recurrence relation, and it's in this form. So here we start from 2 and a1 is 2. So very simple, an is equal to an minus 1. It means 1 previous one plus 3. So for 2, it is 2 plus 3. For 3, so it will be 5. 5 plus 3, which is equal to 8. For this one, it will be simply the previous one, and the previous one is the previous one plus 3. So it comes to here, and it will give us 11, right? So finally, if we do it, we will come with this closed form, 2 plus 3 of n minus 1. So this is a recurrence relation. Simply, you can, draw something like this, and you say n, and the closed form is 2 plus 3n minus 1, right? So for 1, it is 2. For 2, it is 2 plus 3 is 5, right? For the third one, this one plus 3 is 8. For this one, the previous one plus 3 will be 11, and so on. Here is an example of financial application. Suppose someone deposit $10,000 in bank account and he would like to receive yearly interest. The bank say that 11% per year will be your interest. We want to know that after 30 years, for example, how much will be his money. If we consider PN as the amount of the account after 30 years, we need to consider one thing. We need to, after 30 years, it means at the year of 30, the amount is the amount of 29th year plus 11% of that amount. And for 29th years, we need to consider the previous year up to come back to year 1. So here we start, for this case, we start with $10,000, right? So year 1, we have $10,000. In the second year, right, it will be 10,000 plus 11% of 10,000. So whatever is here, right, for example, it will be 11 something, right? Then this one will come here and 11% of this amount will be calculated. Then it will go for the third year, for fourth year, and so on and so forth. So in here, Pn satisfy this relation, Pn minus 1 plus 11% of the amount of the previous year. So at the end of first year, the money will be 10,000 at the end. So this is a start. You can say year 0. In year 1, this is year 1. This is year 2, right? So it means at the end, after 12 months. After 12 months. So we will calculate in this way. So Pn will be Pn minus 1 plus interest of that year. We can say 1.11 of Pn minus 1, right? So P1 at the end of year 1, we have P0, which is 10,000, and plus 11%, right? Then we have for P2, we have this amount multiply interest. We come for this one. And the same, we go, and finally we will come with this amount. So the closed form is this one. Pn equals to 1.11 power of n multiply 10,000. This is the closed form for this one. In such cases, as we see already, we need to find out the closed form. It is important because using closed form, we can simply find all the remaining terms. Given a few terms of a sequence, we can try to identify the sequence. Conjecture a formula, guess a formula, recurrence relation, or some other rules will help us to do something. So we can think about several aspects to find the closed form. For example, we can find out the repeated terms. If we find the repeated terms, then we can think about what is the relation between them. Next, we have to try to obtain a term from the previous term by adding an amount or multiplying, addition or multiplication. We must find out what is the relation of one term with its previous one, or with its previous and two previous, right? So precedence terms always has an impact on the current one, and the current one has an impact on the future one. Then we try to obtain a term by combining. So adding, addition, multiplication, combination, these are the things that we need to think about, right? So how we can add one or two terms to find the third one, or how we can multiply them, or how we can combine them. Then we can think about cycles. If there is some cycle, that there is some repetition. And also we should think about well-known sequences. As already we discussed some geometric and arithmetic sequences, we should think that whether this sequence follow that route or not. By understanding such kind of hints, we can find out the closed form. Once we find out the closed form, then simply we can find the remaining terms. For example, here, we want to find out the closed form. We have this one, and we want to try to find out the closed form for this one. So it starts 1, and you know that 1 can be written by 1 by 1. So it means this is the same, but here it means there is some change, right? As you can see, 1 become 2, 2 become 4, 4 become 8. So it is very simple to understand that here there is some constant change between these two. And simply we can say, okay, an equals to 1, 2 by n. So how it works, this one is equal to 1, 2 by 0, plus 1, 2 power of 1, plus 2 power of 2, plus 2 power of 3, and so on. So this is the 2 power of 0 is 1, and 1 by 1 is 1, then 1 by 2, 1 by 4, 1 by 8, and something. Very simple. This is a geometric progression. In here, a equals to 1 and r equals to 1 by 2. Here is another example, 1, 3, 5, 7, 9. In here, we should see that each term is obtained by adding a 2 to the previous one. So 1 plus 2 is 3. 3 plus 2 is again 5. 5 plus 2, 7. So, same. Then we can think about the possible formula of 2n plus 1. This is called as arithmetic progression. And in here, a is equal to 1 and d is equal to 2, right? So, 2, you can say n and 2n plus 1, right? 2 for 0, it is 2 multiply 0 plus 1 equal to 1. Here, 1, 2 multiply 1 plus 1 is equal to 3. 2 multiply 2 plus 1 equals to 5. 3, 2 multiply 3 plus 1 is 7. So the closed form is 2n plus 1. Here, the terms alternate between 1 and minus 1. 1 minus 1, 1 minus 1. The possible solution can be minus 1 in power of n. This is a geometric progression, and in here, a is equal to 1 and r equals to minus 1. So very simple. N, a, n. When it is 0, minus 1 in power of 0 is 1. When it is 1, minus 1 in power of 1 is minus 1. When it is 2, minus 1 in power of 2 is 1. And we'll repeat. So here, there are some useful sequences. For example, n squared, you can see, n cube, this one, n power of 4, 2 in power of n, 3 in power of n, n factorial, and f of n. Here is conjecture or guessing sequence. Conjecture a simple formula for an if the first term is here. Again, we want to find the closed form. So 1, 7, 25, 79, 241. So how we can find the closed form for this one? In here, the ratio of each term to the previous one approximate of 3. So it means by something multiply 3, right? So we can come up with this one. Here, in power of 1 minus 2 is 1. 3 in power of 2 minus 2 is 7. This is the concept of summation. Summation means simply sum of a sequence, right? We can show this one, we can show by this one or by this one, right? When we say Jn to n, it means J is a counter, start from m and come to n, right? As you can see here, m plus 1 to m plus 3 to n, right? Or you can simply say here in show like this, and in here J is counter, so one time it will be a1, a2, a3, a4 up to an. Or you simply can show this one, so by this one can come to here or here, or you can show like this, J between m and n for aj. It means am and am plus 1 plus something to an. This is summation. So more generally, for a set of S, we can say J in S, where S is the number of the elements, right? So for example, here, when we have R0 plus R1 plus R2 plus R3 to Rn, simply we will put a counter of J which start from 0 and come to n. This is our counter. So from J equal to 0 to n and Rj, this J is counter R0, R1, R2, R3 to Rn. Or here, we have 1 plus 1 by 2, 1 by 3. We can say from 1 to infinity, because there is no n here, from 1 to infinity, right? Or you can say J equals to 1 to infinity, 1 by J. It means 1 by 1, 1 by 2, 1 by 3, 1 by something. Or here we have 2, 5, 7, 10. Aj, where J is in S, this is S, right? This is S. A2 plus A5 plus A7 plus A10. It refers to this one. The same thing we can do for product notation. So in product notation, instead of summation, we go for production. Very simple. Pi is used for production instead of this one that we use for summation. So in here, pi or sigma, we can use it, right? For summation, we use sigma. For here, we use pi. So J equals to m to n, the same. Or here, or in between. And instead of summation, we have multiplication. We had previously learned about geometric progression when we say it is equal to AR squared, and up to ARN, right? So now we want to see the proof. There are two methods in order to prove a geometric series. So we say that if J is equal to 0 to n, if R is equal to 1, sum of this series, sum of the sequence, if R is equal to 1, it will be n plus 1 multiply A. And if R is not 1, then we can go for this one, AR n plus 1 minus A divided by R minus 1. So in here, we want to prove it, right? Suppose Sn equals to sum of Arj, J from 0 to n. To compute Sn, first we multiply both sides of the equality by R and then manipulate the resulting sum. So simply we add R to both sides of this one, R here, right? And when we apply this one, then we will have the sum of, R will go inside, sum of, so 1 R is here, when come here, it will be plus 1, right? Arj plus 1, right? Then by shifting the index of summation, K is equal to, for example, this one we have K equal to J plus 1. Then we will have K from 1 to n plus 1. This n will be, because we consider K as J plus 1, right? So it will be K from 1 to n plus 1, ARK, right? Then by removing K equal n plus 1 term and by adding K is equal to 0, this one, then we will have summation of K from 0 to n, ARK plus ARn plus 1 minus A. Then by substituting Sn, for summation formula that we have, it will be, so this is our Sn, right? Sn plus Arn plus 1 minus A. And then simply we can say that, okay, Rsn, because here we suppose Rsn. Rsn is Sn plus Arn plus 1 minus A. And then simply Rsn will be this side divided by R minus 1 when R is not 0. And for R equal to 0, we will have Sn, J from 0 to n, Arj equals to J of 0 to n of A equal to n plus 1 of A. So very simple, we can come to the. In order to prove geometric series, there is also another method. In here, sum of the terms of geometric progression for first n terms, we will have like this. S of n, the summation of I from 0 to n minus 1 ARI, which is equal to A, AR squared up to here, then For r not equal to 1, it will be like this. Simply, we can write Sn as a plus ar plus the rest of the sequence. Then if we multiply both sides by r, so 1r will be added here up to the end. Then by subtraction of Sn minus rsn and a minus arn, we will have this one. Then just we take a factor form of the right side, right? So if we take factor, then we will have Sn 1 minus r, Sn will be factor, then we will have 1 minus r here. And from a, we will take 1, this one, right? This a will come outside. This should be a. Then we will have Sn 1 minus r equals to 1 minus rn, right? If you do Sn this side divided by this one side, right? Simply then we will have Sn a 1 minus rn divided by 1 by r for r not equal to 1. Here we consider for the cases where r equals to 1. Again, very simple. We consider this one Sn equal to the rest. Then we say that if r equals to 1, then Sn will be a plus a1 plus, because r is 1 here, right? a1 square up to here, right? Then this one can be written as, then this can be written as Sn a plus, because it is 1, a plus a plus a plus plus a. So how many a we have here? N. Then it is n a. Here we see some example to understand both proof methods. If a equals to 5 and r equals 2, then Sn equals to a plus ar square up to ar5, because we have 5 terms, right? So in this case, S of 6 is equal to 5 plus 10 plus up to here, which will be something like 315. The disadvantage of this one is lengthy. It is too lengthy method. If we have, for example, 500 terms, then it will be very difficult to calculate. Here, Sn a 1 minus r square in power of n divided by 1 minus r. Simply, a is 5, r is 2, right? And n, we want to find the 6th term, right? So, simply, S6 equals to this one, and simple multiplication, we will come to 3. The advantage of the second one is fixed steps. No matter how many terms you want, simply we can. So this one is better. So here are some useful summation formula. For example, sum of ARK when k is from 0 to n is this one. For this is this, and k squared is this one. So this is sequence, summation, and product. I hope you understand the topic, and please feel free to ask me if you have any questions. Thank you.